isolated and combined footing. Today we will see in this video a design of isolated footings. These are very commonly used shallow type footings. When a structure is loaded on firm soil, separate individual footings are provided for each columns, which are called isolated footings. These footings can have square, rectangular, or any other shape in plan. They can have varying depth called trapezoidal footing with minimum depth at the edge and maximum depth at the center of the footing. Minimum depth at the edge and maximum depth at the center. This is trapezoidal footing. Or can have uniform depth, or can be step type. This type of footings are usually used when we have enough space and the footing size of different columns does not overlap each other. Okay. If the footing overlap each other, then you will have to go for a combined footing. The size of footing depends upon the bearing capacity of soil. The allowable bearing capacity must be greater than the actual soil bearing capacity, that is P by A. That is A is area of footing where there is no moment acting, okay, where there is only actual load acting on the column, and P by A plus minus mx by zx plus minus my by zy when there are moments acting. Okay. Gross bearing capacity. Total upward pressure acting below the base of the footing due to total weight including, okay, pressure acting at the base of the footing. One, load from the superstructure. Second, self weight of footing. Third, weight of the backfill. Fourth, weight of the overburden if there. Safe bearing capacity. In order to keep the structure safe bearing capacity of the soil is calculated on field at different points and the selection of footing type is done accordingly. The maximum load per unit area which the soil can bear without displacement or settlement is designated as safe bearing capacity of net bearing capacity. Gross bearing capacity minus pressure due to overburden soil is net bearing capacity. Factored upward soil pressure below the base of the footing is that due to the applied factor load and moments. Okay. The design of footing is done for upward soil pressure at the base of the footing for which one way, two way and other checks are done and the required tensile steel is found. Soil pressure distribution under footing. From the rigorous study of soil mechanics, it has been observed that the pressure distribution under a symmetrically loaded footing is not uniform. Okay. Say you have only an axial load which passes through the CG of the footing. Okay. And if the type of soil is clay or cohesive soil, then this kind of pressure distribution will be there. And if the type of soil is sandy or cohesionless, then this type of soil distribution will be there. But for the ease, we assume it as uniformly distributed. Okay. The pressure intensity depends upon the rigidity of the footing, type and condition of the soil. For different types of soil, we have different types of pressure distribution as shown in the figure below, right? Soil bearing capacity. It should be noted that safe soil bearing capacity QA given by the geotechnical consultant to the structural engineer is applicable for service load conditions, as enough factor of safety has been considered in finding QA. Okay, say the factor of safety of 3 is usually considered for finding QA. The calculation of maximum soil pressure Q must include the self weight of footing and the backfill, that is delta P, okay, which is approximately 10% of the actual load, service actual load on the footing. Q, that is actual pressure, is equal to Pu plus delta P divided by A. A is the area of footing. QA should be greater than or equal to Q. Minimum area required, footing area required should be greater than equal to P plus delta P divided by QA. So this is the footing, okay? So this is the backfill, and this is the footing. Weight of these two combined is known as delta P, right? Okay. So distribution beneath the footing for different eccentricities. Various possible um, base pressure distribution are shown in figure below. For the case of uniaxial eccentricity loading on a rectangular footing. Okay. This is, you can see the distribution of upward soil pressure uniform, trapezoidal, triangle. Okay. Okay. In general case, the biaxial eccentricity is possible in case of footing for corner columns of the building. Factor loads and moments are used for finding the factor soil pressure for the ultimate limit state design of footing. Okay. The size of the footing should be so selected that the eccentricity E should fall in the middle third of the footing and respective both about both major and minor axis if the footing has to be designed for biaxial moment. Okay. So this is your E. Then this E should fall in the middle third of this footing, that is L by 6 on this side, L by 6 on this side. Okay. It may be further noted that the soil pressure which induces moment and the shear in the footing base are due to the net pressure, that is excluding the pressure due to the weight delta P of footing and backfill. That is, the net pressure is due to the concentrated load on column from the superstructure and the moment at the base of the column. Okay. So we will take net pressure for designing a footing. Okay. Now in this figure we can see when eccentricity is zero, that is there is no moment. Okay, the upward soil pressure distribution is uniform. Okay, when eccentricity is less than L by 6, L is the length of the footing. Okay, then you will have a trapezoidal type of uh, upward soil distribution. Q mean Q max. Okay, when eccentricity is equal to L by 6, then Q mean will be 0 and you will have only Q max. When eccentricity is greater than L by 6, then some of the portion of the footing will leave the contact with the soil. Okay, only uh, and only say you can see over here that only instead of L, only L dash length is in the is in touch with the soil. Okay, so this alternate is not allowed. Okay, because there is a, you can say there is tilting of footing. Okay, so always try to keep your E less than L by 6. Okay, so you can have this kind of pressure diagram, right? Upper soil pressure. For footing with axial load and uniaxial moment, these are all soil upward pressure due to footing with axial load and uniaxial moment. This, and this. Okay, this is for only axial load. Okay, the Q mean is equal to Pu by A minus M by Z, where Z is the modulus of section, Z is equal to B L square by 6. B is the width of the footing, L is the length of the footing. Q max is Pu A by plus Pu by A plus M by Z, where Z is the modulus of section. For footing with axial load and biaxial moment, okay. So this is the uh, pressure diagram, right? So Q is given as P by A plus minus mx by zx plus minus my by zy. Okay, this is maximum Q maximum. That will be P by A plus mx by zx plus my by zy. This is Q minimum. Okay, that will be equal to P by A minus mx by zx minus my by zy. Okay, so this is how you will have this kind of upward soil pressure in case of biaxial footing with axial load and biaxial moment. Okay. Critical section for finding design moment, check for one-way shear and check for punching shear. So this is the section 1-1 at the face of the column. Section 1-1 at the face of the column for calculation of maximum bending moment for which the footing has to be designed. Okay. This is second section at a distance d by 2, okay, from the face of the column. Section 2-2 is at a distance d by 2 from the face of the column where the check for punching shear has to be done, right? So this is a footing, okay? This is L, this is B, this is column. At d by 2 and d by 2, you get a section like this over here, right? Okay. So this is the periphery, okay? And you can see over here that this column punches the footing over here like this, right? This is at distance d by 2. That is what we consider at section d by 2, okay? And this is effective depth d, okay? Now section 3 at a distance d from the face of the column. Section 3 is at a distance d from the face of the column where check for one-way shear is done, okay? So this is that section, okay, at a distance d from the face of the column where we do the check for one-way shear, okay? So now let us try to solve an isolated footing. Design an isolated rectangular sloped footing for the column of size 230 mm by 525 mm, 230 by 525. Okay. Reinforced, and the column has reinforcement six number of 20 mm dia bars carrying an actual working load of 1000 kilonewton and working moment of 75 kilonewton meter. The soil bearing capacity is 250 kilonewton per meter square. Use M20 grade concrete, Fe415 steel, and effective cover to be considered at the bottom steel is to be 75 mm. It's effective cover. Okay. Okay. So solution: FCK is equal to 20 Newton per mm square. Fy is equal to 415. Service load is 100. Assume weight of the footing and backfill delta P 10% of this, that is 100 kilonewton. Save bearing capacity SBC is given to us is 250 kilonewton per meter square. Eccentricity E is M by P plus delta P. Take M equal to uh, M as your factored moment, that is 75 into 1.5. P is your factored load 1000 into 1.5 and 10% of this, okay, that is delta P, which gives us eccentricity 68.18 mm. Okay, so the length and breadth of the footing are to be so selected that the eccentricity is less than L by 6. Okay, as we seen above, so that the entire footing, entire area of the footing is in contact with the soil. Okay. Now we have to assume the size of the footing. So let us start with this. Area minimum is equal to PU plus delta P divided by QA. Actually, as we have moment also, so it should be PU plus delta P divided by QA plus M by Z. But for simplification of calculation, let us take just PU by delta P. The U plus delta P divided by QA. QA is 250. We get this as 4.4 meter square. Under root of this is 2.1 meter square. Okay. But we know as a moment is also acting with the actual load. So actual pressure will be this plus M by Z. So I am assuming L as 2.4 instead of 2.1, right? I'm assuming a larger L than which is required for this, that is PU by delta P divided by QA, because moment is also acting. So L is equal to 2.4. Okay, so L is equal to 2.4 meters. Now this is the projection A, that is from the face of the column to the footing. Okay, and this is projection B in this direction, right? Now, for getting an economical size of footing, it is necessary that this projection should be kept same. Okay, the A can be easily found. L is known to us. The column width depth is known to us. Okay, so the cantilever projection about the major axis A is L minus D. D is this. Okay, 5 to 5 divided by 2, that is 0.9375 meters. So this is 0.9375 meters. Okay. So assuming the cantilever projection P about minor axis equal to A, assuming B equal to A, so A is known, so B is known, B plus 230, that 0.23 meters. So that is how we get the breadth equal to 2.1 meters. Okay, so B is equal to 2.1 meters and L is equal to 2.4 meters. Now the next step is we have to check that the actual pressure below this footing should be less than the allowable pressure. Okay, so let us check whether the allowable pressure, soil pressure, is greater than the actual soil pressure. So as we see, actual is P U by delta P divided by area of footing plus M by Z. So this is P plus delta P divided by A. This is M, okay, and this is Z, okay. Z is 2.1 into 2.4 raised to square divided by 6, okay. So this is equal to 249.61, which is less than SPC 250. So it is okay and safe. Okay. Now, in case of footing, we don't provide shear reinforcement, right? So it is shear is the main criteria which governs the depth of the footing. Okay, so let us assume the depth of the footing with respect to shear criteria. One way shear along shorter span. Okay, so we are taking this section AA at a distance D. Okay, this is the section AA that is for one way shear, that is at a distance D from the face of the column, and we want to find D double dash. Okay, we want to assume this D double dash. So let us first start by assuming uh, the allowable permissible shear stress tau c. Okay, let us assume permissible shear stress tau c equal to 0.36 Newton per mm square. So from table number 19, IS 456-2000, the corresponding PT for tau c equal to 0.36 and M20 grade of concrete, it is 0.25%. That means at this section, okay, at section A, at this section, the tensile strength to be provided is 0.25%. Okay, that is what we are assuming. Okay, right. So this is the section. Okay, so this section, the permissible shear force which this concrete section can take is equal to tau c, okay, into this D into length B, right? This is section AA shown over here, right? This is B, okay. This is D, okay, and we can see this shaded portion is I have shown over here because this is trapezoidal footing, okay. So from here the depth is decreasing, right? So it is going something like that. And over here it is going something like that. Okay. But for ease of calculation, I am taking it this as a rectangle, okay, because we are just still assuming our D dash, okay, then we will have to actually check whether this D is safe in one way shear and punching shear stress, okay, and if it is not found, then we will have to increase our section, right? So for just assuming our D dash, I am taking this as a rectangular section at this particular section, right, at a distance D. Okay, so we have one equation that is allowable shear force B allowable is tau C into B into D. Okay, just I explain. This is tau C. This is permissible shear stress into D into B. Okay, so this is our first equation, right? Now we know Q max is equal to P by A plus M by Z. Q mean is P by A minus M by Z. So factored upward soil pressure. Okay, this is factored upward soil pressure. So you have to multiply the load factor with the service load and moment, right? That we get as 353.42, and Q mean we get as 241.8. Okay, this is 353.42 and 341.8. Okay, so this stress is over here, okay, and this stress is over here, okay. Now the second equation we can get is we will get another shear force, where shear force actual, right? Due to this upward soil pressure, right? And that shear force should be less than this allowable shear force, okay? If it is not less than, then you will have to increase the D or percentage of steel. So right now it is not possible for us to find Q1 because we don't know D. Okay. So let us assume an average stress diagram just for the purpose of assumption of D dash, D double dash. Okay. So let us take average Q is equal to 297.61 kilonewton per meter square. Okay. Now, as we have taken this as average, okay, now it becomes easy. Q, right, into this, okay, Q into L1 into B. This is the area, okay, which we have to consider, and we have to find the shear force under this area. So this area into Q average will give us the force, right? That is V actual. Okay. So V actual is Q. This is Q average. Okay, just which we found over here. We have to take as Q average. Okay, into L1 into V into B. Okay. Okay, L1 we can find in terms of D. Okay. What is L1? We know this is 0.9375. A is 0.9375. A minus D will be L1. Okay. So L1 is equal to 0.375 minus D. Okay. So put this value of L1 over here. Okay. So we get this as 58591.68 minus 642.98 D. Okay. Now equating allowable V to actual V, that is tau C into PD is equal to this, right? Solving this, we get D dash is equal to 424.3. Okay, D double dash we get is 424.3. Okay, this is what we are assuming. Okay, now we will go on a little bit conservative side and assume our D as 450 mm. Okay, so let us assume the considered at the considered vertical section, that is, this is considered vertical section. Okay, the effective depth is 450 mm. Okay, and this is an average D about major and minor axis. What does this mean? Let me try to explain you. Okay, this is the steel about the length along the length of the footing, and there will be steel over here along the width of the footing, that is these two. Okay, so we are taking average D. Okay, average D means what? This diameter plus this diameter, you have to take the center of this center of the these two diameters. Say this is 12 mm, this is also 12 mm, then 12 and 12 is 24. So you have to take start this line from 12 mm. Okay? So from top to the center of these two scale, okay, that is D average. Okay, so this D average can be used in both the axis, that is minor axis and major axis. Okay, okay. Now we have already assumed D. Okay, so we know this L1 actual L1 now. Okay, so actual L1 is 0.9375 minus 0.45. Okay, so once you know L1, you can find Q1 at this section. Okay, so the Q1, that is soil pressure diagram, Q1 is equal to 330.75. This is found to be 330.75. You can find it easily from doing interpolation, right? Okay. Now, once you know this Q1, you know this Q max. Okay, you can find the V actual over here. Okay, V actual. V actual will be average of these two, Q max plus Q1 divided by 2 into this area. Okay, the area under which the soil pressure is acting, right? This is our section. So we have to find the V actual for the upper soil pressure acting below this area, right? So Q into L1 into B. So that is equal to 350.20 kilonewton. Okay. Now we have to, as I told you, that from V actual we find the nominal shear stress. Okay, and our nominal shear stress should be less than tau c. If it is, because we are not providing shear reinforcement in footings, if your nominal shear stress tau v is found to be greater than tau c, then you will have to increase your T, or you will have to increase the percentage of steel. Okay, so let us take in our case. Okay, minimum depth of the footing at the edge over here we are taking as 150 mm. Okay, the nominal shear stress tau v is equal to V actual divided by cross sectional area of the footing at a distance d. So this is our section 3. Okay. So over here, this is the cross section of the footing. This is our steel. Below that, it is our effective cover. So this shaded portion area will be active in taking in resisting this V actual. Okay. So the area of this shaded portion is 785625. Okay. So V actual is known to us. This into this area, that is equal to 0.446, and our assumed tau c is 0.36. Okay, so we found that tau is greater than tau c, right? So which is not allowable. So either we will have to increase the depth of the footing, or we will have to increase the percentage of steel. The percentage of steel considered is 0.25%, right? So now we will change the percentage of steel, and will not change the area of the section. Okay. So now let us assume that tau c is equal to tau v. So tau v is 0.446. Okay. So we take tau c also 0.446. Okay. So for tau c equal to 0.446, and concrete grade M20 from table 19.456, as 456 2000, we get PT equal to 0.425. So instead of 0.25 percentage, now we will be considering 0.425 percentage of steel. Okay. So now we can find the area of main reinforcement required, that is percentage into area of the section divided by 100, that is equal to 3339 mm square. So this is the steel that is to be provided along the length of the footing. Okay. Now this is for section 4. Now we will have to check our one-way shear on this section, right? That is at a distance d from the column face, that is 450 mm. So this section is at this section, right? This is section 4 4, section 4 4. Okay, the area of this shaded portion is found to be 1041300 mm square. Okay, now let us check one way shear at this section. Okay, right. Okay, so over here, over here, the shear stress is 353.42, and 4241.8 is the stress acting over here, right? So we can take the average of this. Okay, average, we can take average of this, right? So average of this is equal to this plus this divided by 2, that is 297.61, right? Okay, now we want to find, once we have found Q average, so this is the area, okay, under which this soil pressure acts. Okay, this is the area beyond the section. So Q average into this area. So what is this? This is B from the face of the column minus 450, B minus 450. This is B minus 450, right? So this is how you can find Q average. That is equal to 346. You can find V actual. Okay, V actual, which will be acting at this section, right? So that is found to be 346.41 kilo Newton. Okay. So now again following the same procedure, finding tau v is equal to V actual divided by cross sectional area of the footing at a distance d, which is this area. Okay, that is, we are considering this section over here. This section 4, this is section 4 4. Okay, so this is how we get this equal to 0.3326. Okay, so 0.3326 is less than tau c. Tau c is 0.36. Okay, so it is as the tau c is as the tau v is 0.3326 and tau c is 0.36. As tau v is less than tau c, so it is safe. Okay, so we had considered the percentage of steel for this tau c as 0.25, okay, PT. So we will continue with the same percentage of steel. So the area of main reinforcement required for the purpose of the shear ESC is equal to percentage of steel into area of section, okay, divided by 100. That is 2603.25 mm square. So this is the steel area that is to be provided along width. Okay. Now we will go for check for two way. Now D is equal to 450 mm. Okay, depth of column is 525 mm and width of the column is 230 mm. Okay, so 525 mm and width is 230 mm. Okay, right. Now first step is we have to find the peripheral length. Okay, so peripheral length. So this is the column. We know that for finding the punching shear stress, we have to take the section at a distance d by 2. So this is d by 2, 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 right? So this is 525 plus d by 2 plus d by 2, that is d. So 525 plus 450 is the length of this. Okay. Now this is 230. Okay. So this is d by 2, this is d by 2. So this is 230 plus 450. Okay, that is this line, right? So peripheral length will be 230 plus 450 into 2, that is this plus this. 525 plus 450 into 2, that is this plus this. Okay, so we get that equal to 3310 mm. Okay, so the peripheral length is 3310 mm. Okay, now we will take Q average. Okay, so okay. Uh, this is the actual stress diagram, actual upper soil pressure diagram below the footing. Okay. For ease of calculation, we can take average of these two. Okay. Average of these two is 297.61. So we will consider that an average stress diagram of average pressure of upper soil pressure is 297.61, which is acting below this footing. Okay, so it becomes easy for the calculation, and the results obtained by applying this stress or this stress will be the same. Okay, so we are taking the average stress like this. Average soil pressure, upper soil pressure, as shown in this figure, right? So which is applied over here. Okay, now we can see this peripheral area is shown over here, right? This is a peripheral length. This is 525 plus 450, and this is 230 plus 450, right? Now this peripheral length into D, D is the depth of the footing at this section. Okay, effective depth at this section, that is D. Okay, this is D. So this is the peripheral area which will take the punching shear force. Okay, or okay. So now we have to find the shear force. Simple. This is the upper soil pressure acting below the footing. So this pressure Q, that is in kilonewton per meter square, into this total area of footing minus the area inside the periphery. Okay, that is how you get the area outside the periphery, right? So that area into this will give you the shear force. Okay, so you can see over here. Okay, first we have found Q average. Okay, this is Q average, that is 297.61. Now shear force B, Q average into area of footing minus area of peripheral area. The area in the periphery. Okay, so that will give you the shear force Q 1302.63. This is shear force which the this section has to take, right? This section has to take. Okay, simple. So nominal shear stress tau V is V divided by peripheral length into D. Okay, peripheral length into D. Okay, so this is how we get this as 0.8745. Okay, Newton per mm square. Now allowable shear stress in case of punching is Ks by tau c. Ks is equal to zero point 0.5 plus beta c, where beta c is the ratio of smaller side of the column to the longer side of the column. Okay, where smaller side is 230 mm, longer side is 525 mm. That is equal to 0.438. Okay, so zero point 0.5 plus 0.438 is 0.928. Okay, but Ks cannot be greater than 1. Okay, as this is less than 1, so it's okay. Say suppose it were greater than 1, then we would have to take a 1, right? But our value is coming out to be less than 1, so we will take the actual value 0.928. Now tau c is equal to 0.25 into under root FCK. FCK is 20. So we get this as 1.118. So this into this is equal to 1.04. This is our allowable shear stress. Okay. The shear stress which this section can carry. Okay. But the actual shear stress is 0.874345, which is less than allowable. So it is safe. Okay. So now we found that our footing section is safe in both one way and two way shear. Okay. So now we will have to go for uh, we will have to find the moment, and for moment we will have to find the speed that is to be provided, right? So moment, for finding moment, we have to take our section at the face of the column. Okay. So this is the section at the face of the column. This is our D, that is 450 mm. This is L1, which we know, right? That is 0.9375 meters. This is B, which we know, that is 2.1 meters. Okay, right. So we can find this Q easily. Okay. Well, the soil upper soil pressure over here is 353.42, and soil upward pressure over here is 241.8. This is Newton per mm square. This is kilonewton per mm square. Okay, it's in basic, please. Kilonewton per mm, kilonewton per meter square. Kilonewton per meter square, please. Uh, okay, don't get confused. Okay, it's kilonewton per meter square, right? Now L1 we know 0.9375. Okay, and B we know 2.1 meters. Okay, so you can find by interpolation Q. Okay, very easily. So Q is found to be 309.8 kilonewton per meter square. Okay, so once you know this Q, you know Q max, you can find the bending moment due to this upward soil pressure at this section, which is at the base of the column. Okay, so you, what can you do? You can just divide this trapezoidal upward soil pressure diagram into two parts. That is, one is rectangular and another is triangle. Okay, so let us find the moment about the this section. So the moment due to this pressure diagram will be Q into L1. This is L1. Okay, into B. Okay, so this is the area, right? This is the area under which this upward soil pressure is acting. So this area into Q, okay, that will give you force over here at the CG, and that force into L1 by 2 will give you the moment. Okay, so that is what this gives, right? Now you take the triangular portion. Okay, similarly, this will be Qmax minus Q. Okay, that is this. Okay, into L1 into zero point 0.5 is the area of this triangle, into B is the total area. Okay, and you get the total force acting at this CG. Okay, so this that force into 2 by 3 L1 will give you the moment about this cross section. Okay, so this is what gives that moment. Okay, so the total is found to be 312.73 kilonewton meter. Okay, so this is the moment which is found to be uh, at this section at the face of the column. Okay, now this next step is we have to check whether the D provided by us is greater than the minimum required. Okay, so for balance section we know M is equal to 0.138 FCK BD square. Okay, when your FCK is 20, so D is equal to under root M by 0.138 FCK into B. So this is found, D is found to be 232.28, and we have provided 450 mm, so it is required D is less than provided, and that concludes that our section is underreinforced. Okay, so we can find the steel using this formula. So we know the moment, that is 312.73. Okay, put the value of moment over here. D is equal to 450. You find steel equal to 205 2015 mm square. Okay, but now we have to check that whether this steel is adequate for taking the one way shear criteria, satisfying the one way shear criteria. Okay, so but the AST required for one way shear was 3339 mm square. Okay, Let us just refresh our memory. Going back, okay, okay. So this for this section, okay, we found that the steel required was 0.425% to satisfy the one-way shear, and the area required was 339 mm square. So we have to provide the larger of the two. Okay, this is what this is what we require to satisfy the moment criteria, and this is what we require to satisfy the one-way shear criteria. So we will provide this area of steel. Okay, so let us assume 12 dia bar as main steel along the length of the footing. So spacing is is found to be 71 center to center, but we will provide 12 dia bar about 70 center to center. Okay, so this is the detailing. Okay, we can see the bars along the length are should be provided at 12 dia about 70 center to center. Okay, you can see this section. This is the main steel, 12 dia about 70 center to center. Okay, okay. Now we can see we have taken average D. So I have written D equal to 450, and D here also D should be equal to 450 because we have taken average. Sorry, it's a mistake. Uh, D is over in this direction also is taken as 450. Okay. Now coming to the finding the moment about this phase now. Okay. Now we take a section over here, right? At this face of the column, and so we want to find the moment. So the area beyond this section will be B. This is B, so this is B into L. Okay, so that is the area. Okay, that which will give which will give a force, and that force will give a moment about this section at the face of the column. Okay, okay. So right, this is the section I have shown at the face of the column. Okay, so over here the uh, stress upward soil pressure is 353.42 kilonewton per meter square. That is over here. Okay, over here, right? And over here it is 241.8. Okay, 241.8. Okay, so we can take average of this. Okay, that average will be 297.61. Okay, so this is the upper soil pressure acting below the footing. Okay, this is B1. Okay, this is B1. This is B, which I have called as B1 over here. Okay, which I have called B1 is equal to B. Okay, so that is 0.9375 meters. Okay, so very simple. This L into B is the area into Q average will be the force acting at this point, right? Okay, so Q max plus Q mean divided by 2, that is this average. Okay, into B1, that is our small b. B1 and B are the same. Okay, into L. Okay, that will give a force, upward force, actual force due to the upward soil pressure, right? That force into B1 into 2 will give the moment about the face of the column. Okay, so that is found to be 312.21 kilonewton meter. Okay, so putting the value over here, we find AST required is 2001.55. Okay, but the AST required for one-way shear condition was 2603.25. Okay, that is 0.25%. Okay, so let us refresh our memory. Just going back. Okay, right. So we are finding the moment over here, right? Okay. So in this case, the percentage of steel required at this section was tau v was found greater tau c was found greater than tau v, and for this tau c we had assumed percentage pt 0.25. Okay. So as according to that percentage of steel, okay, we got as according to 0.25% steel, we got the area of steel as 2603.25 mm square. So we have to take greater of these two. Okay, so this is greater. Okay, so you, from this we can find the spacing. Okay, spacing is found to be 121.61. Okay, sorry, 122.61 mm center to center. We are providing 12 diabars. Okay, the spacing required is for 12 diabars. The area of 12 diabar is 113, right? Okay, so now we will provide 12 diabar at a spacing of 120 We are rounding off. Instead of 122.61, we will provide our steel 12 diabar about 120 center to center along the width. Okay, this is along the width. So 12 dia about 120 center to center. Okay, so this is our steel. Okay, that is 12 dia about 120 center to center. Okay, so this is how we did the design of trapezoidal footing, isolated footing. Okay. Now comes the last step, that is check for bearing pressure. Okay, transfer of forces from column base at the column base. Factored compressive force at the column base is 1.5 into 1000, that is 1500. Limiting bearing stress of the column at the column footing interface should be 0.45 FCK into under root 1 A1 plus A2, where this has to be uh, uh, greater than equal to 1 and less than equal to 2. Okay. So what is A1 and A2? A2 is the area under the column. Okay. And A1 is the area which has to be found by this one gem 2. Okay. And drawing the incline line, and whatever wherever this line cut the footing. Okay. And then the area of this at this level. Okay, that is that is has to be taken as A1. Okay, so in our case A2 is 0.525 into zero point 0.3 and A1 is found to be zero point 0.9 by zero point 0.9. So A1 by A2 is found to be 0.2589. Okay, but this cannot be greater than 2, so we have to take this as 2. So putting the value over here, we get limiting bearing stress column footing in at the column footing interaction surface as 0.45 into 20 into 2, that's 18 Newton per mm square. The actual bearing stress is factor load by column base area. Factor load is 1500 kilonewton. When you convert it into Newton, it will be for 1500 into 1000 divided by 525 into 230, that is equal to 12.42 Newton per mm square, which is less than allowable, so it's okay. So when code says that though our actual bearing stress is less than allowable, still you have to at least provide continue four diameters of the column at the corners of the stirrups or ties, you can say, they are to be continued in the footing. Okay, but in our case, we will continue all the six longitudinal bars of the column into the footing, which is a regular practice. All the steel, longitudinal steel of the column are continued in the footing. Okay, and they're continued in the footing for a length equal to development length. At least, if it is greater than, it's good, but at least the this length should be LD. Okay, so the developments required for 20 bar in compression, M20 and Fe415. For 20 diameter, it is 752. Okay, so extend all the bars of the column into the footing, right? So at least the length which is extended in the footing should be greater than this. Okay. So this was the design of isolated footing. Uh, Now you can also use this program for finding for designing the footing. Okay, it's an such programs can be very useful. Okay. 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 SBC, you have to give our SBC is 250 plus step. Okay, sorry. Okay, service load is 1000. Service moment is 75. Other service moment is 0. Length of column is 0.525 meter. Length width of column is 0.23 meter. F5 is 415. FCK is 20. Okay. So the program gives an footing size, length, and width. Let us take our actual. Okay. So uh, delete. Okay. Let us delete this. And our is L is 2.4. Delete. This is 2.1. Assume PL. Okay, PL is this, which we have assumed as 1.1425. Okay, this is 1.1425. Okay, now this is PW, which we have assumed as 1.13. Okay, and depth we have assumed as 0.52. Okay, 5. Our effective depth is 450. Okay, and cover is 75, so it will be 525 will be the overall depth, right? So you can just click and get the values. If we are using 8 mm diameter, what will be sorry, I have made a mistake over here. It should be point over here. Okay, and let me correct 415 tab. Okay, so let me again change the values. 2.4, sorry, this is 2.1, this is 1.1425. Okay, this is uh, 1.13. We are considering D as 0.525. Okay, that's where it's calculated. Okay. So, number of bars required if you are using 12 mm dia, 10 mm dia, 12 mm dia, 16 mm dia, and 20 mm dia. You can change these values and get the most economical section by the bar charts will be shown over here. Okay. So this program can be useful for designer of an economical coding. Okay. So I hope you must have find this video useful. Thank you.